Derivation of the multiplication rule from conditional probability. Welcome, everyone. Let's begin our session by revisiting some of the foundations we've already covered. In our previous lesson, we explored what happens when two events occur at the same time, what we call the simultaneous occurrence of two events. In mathematical terms, we represent this overlap, or this intersection, using the notation E intersection F. Now, a common question arises. How do we actually calculate the probability of that intersection happening? To find the answer, we need to rely on a very important concept called conditional probability. In today's tutorial, we aren't just going to use the rule, we are going to understand where it comes from. I will guide you through a step-by-step mathematical derivation to show you exactly how we arrive at the multiplication rule. By the end of this, you'll see how the definition of conditional probability leads us directly to this powerful tool for solving complex probability problems. Understanding the starting point, conditional probability. Now, before we jump into the actual derivation we saw promised on the previous slide, we need to ground ourselves in a fundamental concept. Let us take a moment to recall the definition of conditional probability. Think about the notation first. When we talk about the probability of an event E occurring, specifically under the condition that event F has already taken place, we denote this as P of E given F. That vertical bar simply represents the condition we are assuming to be true. To see how this works mathematically, let's look at the formula. The probability of E given F is defined as the probability of the intersection of E and F, divided by the probability of F. In other words, we are looking at the overlap of both events relative to the occurrence of the condition itself. However, there is one very important mathematical constraint to keep in mind. This formula is only valid provided that the probability of F is not equal to 0. We cannot divide by 0, so event F must have some possibility of occurring for this conditional relationship to exist. Keeping this definition in mind is crucial, because in the next slide, we are going to rearrange this exact equation to reveal the multiplication rule. Derivation step by step. You can think of the multiplication rule not as a brand new concept, but essentially as a simple rearrangement of that conditional probability formula we just looked at. Our goal here is to rearrange the equation to isolate the joint probability, which is the probability of the intersection of E and F. Let's break this down into two scenarios. First, let's look at case A, where we assume event F occurs first. Suppose we want to find the probability that both E and F occur, and we already know the probability of F and the conditional probability of E given F. To derive this, we follow three simple steps. Step 1, we start exactly where we left off, with the definition of conditional probability. That is, the probability of E given F equals the probability of E intersection F divided by the probability of F. Step 2, to isolate our target, the probability of E intersection F, we need to get rid of that denominator. So, we multiply both sides of the equation by the probability of F. This gives us the probability of F, multiplied by the probability of E given F, equals the probability of F, multiplied by the probability of E intersection F, all over the probability of F. Step 3, now, we simplify. On the right side, the probability of F in the numerator and the denominator cancel each other out. This leaves us with our first version of the rule. The probability of E intersection F equals the probability of F, multiplied by the probability of E given F. But what if the order is reversed? That brings us to case B, where we derive the rule based on event E occurring first. The logic remains identical. Step 1, we start with the definition of conditional probability. But this time for F given E, this means the probability of F given E equals the probability of F intersection E, divided by the probability of E. Step 2, now, a quick reminder of a fundamental rule from set theory. The intersection is commutative. This means the probability of F intersection E is exactly the same as the probability of E intersection F, so our equation becomes the probability of F given E equals the probability of E intersection F, divided by the probability of E. Step 3. Just like before, we isolate the intersection by multiplying both sides of the equation by the probability of E. This gives us the probability of E, multiplied by the probability of F given E, equals the probability of E, multiplied by the probability of E intersection F, all over the probability of E. Step 4. Finally, we simplify the right side by canceling out the probability of E. This leaves us with our second version of the rule. The probability of E intersection F equals the probability of E, multiplied by the probability of F given E. As you can see, both cases lead us to the same result. We can find the probability of both events happening by multiplying the probability of the first event by the conditional probability of the second event. In the next slide, we will see how to apply these derived formulas to a real-world example involving marbles. Now that we have recalled the definition of conditional probability from the previous slide, let's get into the heart of this tutorial, the actual derivation. Real-world, illustrative example. Now that we have seen the mathematical derivation on the previous slides, let's move from theory to practice. To understand how this derivation works in a real-world context, let us consider a scenario involving a bag of marbles. Here is our scenario. Imagine a bag containing 3 red marbles and 2 blue marbles. You are going to draw 2 marbles, one after the other, and it is crucial to note that this is done without replacement, meaning once you take a marble out, you do not put it back. To apply our rule, let's define our events clearly. Let event E be the event that the first marble drawn is red. Let event F be the event that the second marble drawn is blue. Our goal is to find the probability that both these things happen, that the first is red and the second is blue. In mathematical notation, we are looking for the probability of E intersection F. Let's walk through the step-by-step calculation using the rule we just derived. First, we need to find the probability of event E. Since there are 5 total marbles in the bag and 3 of them are red, the probability of E is 3 over 5. Next, we need to find the conditional probability of F given E. This is where the without replacement part is so important. If we assume that the first marble drawn was indeed red, we have to update our bag. There are now only 4 marbles left in total, and since we haven't picked a blue one yet, there are still 2 blue marbles available. So, the probability of F given E is 2 over 4. Finally, we apply the multiplication rule we learned in the previous steps. We multiply the probability of the first event by the conditional probability of the second. So, the probability of E intersection F equals the probability of E times the probability of F given E. Plugging in our numbers, we get 3 over 5, multiplied by 2 over 4. This gives us 6 over 20, which simplifies to 3 over 10, or as a decimal, 0.3. As we move to the next slide, keep this calculation in mind, as we will discuss some common pitfalls to avoid when working with these types of dependent events. Common mistakes to avoid. First, a very frequent mistake is confusing the probability of E given F with the probability of F given E. It might look like a simple swap of letters, but in probability, the order of the condition is crucial. Remember, the notation P of E given F represents the probability of event E occurring specifically after event F has already taken place. On the other hand, P of F given E is the probability of F happening after E has occurred. As we saw in our marble example, these two values are rarely equal, so always pay close attention to which event is the given condition. Second, do not ignore the mathematical condition that the probability of F must not be equal to 0. If you look back at our derivation in slide 2, you'll remember that the formula for conditional probability is a fraction with P of F in the denominator. In mathematics, we cannot divide by 0. If the probability of your first event is 0, the conditional probability becomes undefined. In such a case, the joint probability, or the probability of both events happening, will simply be 0. Finally, always be careful about using the wrong order in your calculations. When you are working through a sequence of events, always ensure that the conditional probability you choose matches the chronological order of the events. If event E happens first and then event F follows, your formula must reflect that specific sequence. Now that we have seen how the rule is derived and how to apply it to a real-world example, I want to pause and discuss some common pitfalls. Even when you understand the formula, it is very easy to make small errors that lead to incorrect answers. Keep these points in mind as we move to our final slide to summarize everything we have learned today. Key takeaways. First, remember that the primary purpose of the multiplication rule is that it provides us with a reliable method to calculate the probability of the simultaneous occurrence of two events. That is, finding the probability that both event E and event F happen together. As we saw in our step-by-step derivation on slide 3, it is crucial to remember that this rule isn't just a random formula. It is derived directly from the very definition of conditional probability that we reviewed at the start of this session. To ensure you can apply this to any problem, keep these two equivalent forms of the rule in your notes. The first form is, the probability of E intersection F equals the probability of F, multiplied by the probability of E given F. The second, equally valid form is, the probability of E intersection F equals the probability of E, multiplied by the probability of F given E. Both will lead you to the same correct answer, as long as you are consistent with your order. Finally, keep in mind that this rule is a fundamental tool in your mathematical toolkit, especially when you are dealing with dependent events. A classic example of this is the sampling without replacement scenario we explored with the marbles in our illustrative example. All right, we have reached the end of our tutorial, so let's wrap everything up by reviewing the key takeaways from today's lesson. I hope this derivation has made the relationship between intersection and conditional probability much clearer. Great job today.